So for today, we will discuss about equilibrium. So yesterday and last week, actually what you learned is the basics of statics. Yeah, the basic of statics. Okay, all the things that you need to know prior to learning about statics. Okay, but starting from today, we will study about the things, the main things, the main core of statics. Okay, the first thing that you need to know is equilibrium. Okay, the first thing that you need to know is equilibrium. In statics, we base all of our analysis based on equilibrium equation. Okay, what is actually equilibrium equation? Equilibrium equation is actually based on the first Newton law. Okay, the first Newton law. Hearing Newton law pertama itu apa ya, Dirnya? Hukum Newton pertama itu apa ya?
Misalkan ada benda yang diam ataupun kecepatannya konstan, maka F sama dengan 0. Resultan F sama dengan 0.
Nah, itu kamu kebalik ya. Oke, jadi saat resultan F sama dengan 0, benda diam akan tetap diam. Oke, benda bergerak akan bergerak lurus beraturan, artinya bergerak dengan kecepatan konstan. Oke, so that's the first thing, and that's the thing that we will talk about all the time from the beginning. Okay, from the beginning until the end of statics. Okay, so we will talk a lot about the first Newton law as well as the third Newton law. Okay, so basically when we talk about equilibrium condition in two-dimensional case means all the forces, all the body, we can simplify it into two-dimensional condition. Okay, so basically you can solve everything on that one piece of paper without needing drawing a three-dimensional case. Okay, for two-dimensional case, okay, the equilibrium condition is actually like this. That's the equilibrium condition that you need to follow. Okay, sigma fx equal to 0, sigma fy equal to 0, sigma moment equal to 0. So you will have three equilibrium equation. Okay, you will have three equilibrium equation. I will talk one by one about what is this, and what is this. Okay, so basically, when we talk about two-dimensional condition, normally we will talk about this coordinate x and y. Okay, when you have your case can be drawn into only x and y coordinate. For example, we have this particular body, for example, and there is a hinge over here. Okay, it's connected to hinge. Then there is force here, F1 equal to 10 Newton, and there is another force, F2 equal to 20, not equal to 20, F2, which is not known yet. And you are asked to solve the value of F2. So this is one of the example of the problem. Okay. What I mean by two-dimensional cases, you can draw your problem and you can solve your problem with only two coordinates, x and y. Okay, when you have to add another coordinate, another axis. Okay, when you have to add another axis, which is the z-axis. Okay, in that case, your case is not your case is not two-dimensional case anymore, which means you need to use a three-dimensional equilibrium condition. Okay, but in most of the cases that we will solve in statics class, it will be two-dimensional. So the problem can be solved with only two axes, x and y. Okay, but you need to know that in real life, most of the case that we have to solve is three-dimensional. For example, like this: x, y, z, and the same problem, but now what you have is a box like that. Okay, the box has three-dimensional hinge there. Okay. And like that. So F1 is known as 10 Newton, F2 known as well 20 Newton, F3 is unknown, for example, and you have to solve for this particular problem. Okay, this one is three-dimensional case. Okay, the left one is two-dimensional case. Okay, what's the difference between two-dimensional and three-dimensional? When we talk about the equilibrium in two-dimensional case, we only need to use three equations to solve it. What are those equations? Sigma fx equal to 0, because in order for the things to be in equilibrium state, in a stable state, okay, the total force in the x direction is supposed to be equal to 0. Besides that, the total force in the y direction is supposed to be equal to 0 as well. And the last thing, the sigma moment, the total moment, which is happening at the body, everywhere in the body is equal to 0. Okay, we only use three equations, but in 3D case, it's more complex. Why? Because we have three axes. So because we have three axes, of course, the force equilibrium, we have three as well. Sigma fx equal to 0. Then we have sigma fy equal to 0. Sigma fc equal to 0. What else? We have three moment equilibrium as well. Okay, we have three moment equilibrium. Sigma moment x equal to 0, sigma moment y equal to 0, and sigma moment c equal to 0. So basically, when we talk about statics, we will talk about equilibrium. Equilibrium means the condition when all the forces and moment which is happening in a body is in an equilibrium state. So the total force is equal to 0. The total moment is equal to 0. Okay, that is equilibrium condition. And we will use this equilibrium equation, 2D and 3D, from now until the end of our this semester. Okay. Yes, Ali Ardi, do you want to ask question? Ali Riyadi? Hello? Okay. Now, let's continue. But before we talk about equilibrium, Okay, the first thing that you're supposed to know is how to draw what we call as free body diagram. Okay, free body diagram. What is free body diagram? Okay, it's kind of diagram which show the body, the system that we want to solve, only the system that we want to solve, and all the external forces which is happening to that particular system. Okay, that is free body diagram. And in order to solve a statics problem, we have to know about the free body diagram first. Okay. Have anyone here learned about free body diagram in physics? I just want to check the things that you have learned in physics. Zakia, di fisika itu apakah free body diagram sudah dipelajari atau belum?
Kayaknya belum deh. Tapi
Belum.
di PRD udah.
Di PRD ya, oke ya. Di PRD, cuman PRD itu okay, for your information, in the Introduction to Engineering and Design, I believe you have learned little bit about free body diagram, but the free body diagram that you learn there is just the basic, very basic one, because you're supposed to know about free body diagram from this class. Okay. Okay, now let's see some example of free body diagram with certain force system. Okay, let us see together. Okay, you can see the first one, the first example here is a free body diagram of a stone with collinear force system. What is collinear force system? It means that all the forces happening on the same line of action. As you can see here, all the forces happening on the same line of action. Because it's happening on the same line of action, you can use only one equation is enough. As long as you make that line of action, okay, as one of the axis, in this case is x-axis. Okay, if we assume that that line of action become our x-axis, then we can solve it using sigma fx equal to 0. Okay, the summation is easy because all the forces happening on the same line of action. So you can just sum it using a scalar summation. Okay. The second one is free body condition, free body diagram example. When the force system which is happening on the stone is concurrent at a point. What does it mean? It means that all the force, all the line of action, the forces happening on that stone, if you trace it, it will go, it will meet in one point O there. Okay, the line of action of F1, the line of action of F2, F3, and F4, all those line of action will meet at O. Okay, in that case, there will be no moment because all the line of action met at one point. There will be no moment, but you have to solve it using two equations in order to solve this particular problem. Sigma fx equal to 0 and sigma fy equals 0. Okay. Later I will re-explain about this. This is just giving you some explanation, some example. Okay. The other example of the free body diagram is parallel. Is a stone with a parallel force system. Okay. Actually, this is the same as the the previous problem, yesterday's problem that we solved at the end of the class. Okay, in this case, because all the forces happening to the x-axis, okay, then the equilibrium condition, we can solve it using this two equation: sigma fx equal to 0 and sigma moment equal to 0. Okay, remember, we won't be able to solve it just using sigma fx equal to 0. Why? Because the line of action of all those forces are not the same, are not exactly the same. All of those not exactly the same. Okay, and the last one is general. The general one. The general one is the one that normally we will face the most. Okay, we have force, we have external forces, we have external moment as well, which is happening on the stone. Okay, not necessarily the force will meet each other in one point like that. Okay, so for this kind of condition, okay, we can solve it using all of those three equations that we have: sigma fx equal to 0, sigma fy equal to 0, and sigma moment c equal to 0. Okay, so this is the example of free body diagram. As you can see there, okay, jadi ini adalah contoh-contoh dari free body diagram ya. Jadi diagram benda bebas. Bahasa Indonesianya adalah diagram benda bebas. Nah, bisa kalian lihat di situ contoh-contohnya itu macam-macam. Ini bisa dilihat yang contoh pertama itu adalah suatu benda, suatu batu ya. Dia free body diagram dari suatu batu dengan sistem gaya yang bekerja itu kolinear. Pas semua garis kerja gayanya sama. Yang kedua, itu gaya-gaya yang bekerja bertemu di satu titik, di O. Oke, untuk yang pertama, kita bisa menyelesaikannya dengan sigma fx sama dengan 0. Kita asumsikan bahwa garis kerja gayanya adalah aksis X, ya, sumbu X, seperti itu. Kemudian kalau yang kedua, yang concurrent head point ini, kita bisa menyelesaikan dengan menggunakan sigma fx sama dengan 0 dan juga sigma fy sama dengan 0. Seperti itu. Karena tidak ada momen di sana. Ya. Lalu, contoh yang ketiga adalah free body diagram dengan sistem gaya yang bekerja paralel. Nah, bisa dilihat di situ gayanya bekerja ke arah X semua. Oleh karena itu, kita bisa menyelesaikan equilibriumnya dengan sigma fx sama dengan 0 dan juga sigma moment sama dengan 0. Ingat, sigma fx sama dengan 0 tidak cukup untuk menyelesaikan kasus ini karena garis kerja gaya dari keempat gaya yang ada di sana tidak sama semua. Oke, lalu yang terakhir, ini yang paling sering kita jumpai, itu adalah kasus general, kasus umum. Itu gaya-gaya yang bekerja belum tentu bertemu di satu titik, kemudian ada momen juga, jadi kombinasi antara gaya dan momen. Nah, ini kita bisa selesaikan dengan menggunakan sigma fx sama dengan 0, sigma fy sama dengan 0, dan juga sigma moment sama dengan 0. Seperti itu. Oke. Nah, okay. So one thing that you're supposed to remember when you take a look at this free body diagram, okay, you can see, right, when we draw free body diagram, we are not drawing the hinge anymore. What we draw there is just the it's just the external forces which is happening to the body. Okay, external forces and the gravitational forces which is happening in the body. So we are not drawing the hinge anymore. We are not drawing the support anymore. Okay, we are not drawing the hinge anymore. We are not drawing the support anymore. What we draw there is just will be just the external forces which is happening to the body, as well as the gravitational forces which is happening to the body. Okay, you can see, right? There is no hinge there. There is no support there. What we have there is just forces, moment, and maybe gravitational forces. Oke, jadi bisa dilihat di situ ya, di free body diagram yang sudah kita lihat di sini. Sesuatu hal yang spesial di sana adalah kita tidak menemui adanya pin di sana. Kita tidak menemui adanya support di sana. Yang kita temui itu hanya gaya-gaya luar, gaya-gaya gravitasi, dan juga momen saja. Seperti itu. Ya. Jadi di free body diagram itu haram hukumnya untuk kita menggambarkan support-support yang ada. Support yang ada, terus boundary condition yang ada, itu harus digantikan dengan gaya luar. Seperti itu. Itu yang harus kalian lakukan. Oke. If sorry. Yeah, this is some of the problem example that we will discuss in the next 2 weeks. Okay. Now, I think we will try to solve together this particular problem. Okay, the two-dimensional problem, problem number 1. Okay, how can we draw the free body diagram in order to solve for F2 like that? Okay. Just now, I remember that I told you guys that we cannot draw the hinge anymore, and we supposed to replace the hinge with external forces. Okay. When we talk about pin like this, okay, when we talk about pin like this, okay, we can replace the pin with force in 2 directions, X and Y, like that. Okay. So just now we have this, right? And it has pin over here. And force like this. Okay, F1 is 10 Newton. F2 is unknown. Okay, in order to solve for F2, for example, in this case, the first thing that we're supposed to do is to draw a free body diagram. Okay, how can we draw the free body diagram? Remember, the first important rule about free body diagram is you are not supposed to draw the hinge anymore. You are not supposed to draw the support anymore. Okay, you have to replace the hinge and the support with the external forces, which is representing the hinge. So, if we want to draw the free body diagram, then we draw the body that we want to solve. So, in this case, is this. Okay, then we draw the external forces which is happening there. F1 is known, 10 Newton. After that, F2, still unknown, the value. And then at the hinge, what we supposed to draw at the hinge? What we supposed to draw at the hinge? Judy?
Yes, sir.
What we supposed to draw at the hinge?
A force.
Only a force or 2 forces?
2 forces, sir.
In what direction and what direction?
I think in the directions of F1 and F2.
Actually, the best one is to draw it in X and Y direction. Or yeah, actually, you can draw it in 2 forces, which is perpendicular to each other. When you have pin like this, okay, remember, pin works like a hinge in on your door. Okay, so basically, it restrains the movement in X and Y direction. So when you have a pin like this, okay, you can either draw a force like this, Fy, Fx to represent the pin. Or if you don't like it to make the force like that, and you want to make it, you want to have this as your x direction and this as your y direction, you can do it as well. So you can draw the forces at the pin like this. Fx, Fy. So basically now we are using this as our coordinate. So basically, when you are talking about pin, okay, the forces that should represent the pin, it's supposed to be two forces perpendicular to each other. Okay, so this is the free body diagram that we can use. Then after we are drawing the free body diagram, what we're supposed to do? Still Judy. Hello, Judy. Where is Judy? Judy is gone. Okay, then in that case, Nabil. Nabil FR. Oh, Nabil.
Yes, sir.
Okay, Nabil. After we draw the free body diagram like this, what we're supposed to do? Nabil? Remember, right? We want to solve for F2. We want to solve for F2. And the first thing that we're supposed to do is to draw the free body diagram. Okay, the next thing that we're supposed to do is what? We are talking about static here. So in order for this particular body to become in the to be still in the static condition, okay, we have to check it with equilibrium condition. Equation, okay, to see whether the equilibrium condition fulfilled or not. Okay, Nabil?
Yes.
Okay. Would you mind to state what are the equilibrium equation that we're supposed to use here?
Is it sigma f equals 0?
Sigma f what? We have two sigma f, Nabil.
Fy then, because
Sigma fy equal to 0. What else? Do you need sigma fx equal to 0?
I think so.
Yes, of course, you need it as well. Okay. If you are confused about the problem that you are solving, always use this one, general one, the general condition, because most of the time, if you use the general condition, you will be able to solve it. So always use the general condition first. So we have sigma fx equal to 0, sigma fy equal to 0. What else, Nabil?
Sigma
Moment.
Okay,
equal to 0.
Z is 0.
Yeah, sigma moment z equal to 0. Sigma moment z means that the direction of the moment is going through the paper or going out of the paper. So we can just use sigma moment there. Actually, it's representing the sigma moment z equal to 0. Okay, we can solve it using these three equations. After that, okay. Remember, we are using this as our coordinate, and if we assume that this is in the x direction, if this is in the x direction, This is in the y direction. This is in the y direction. Okay. And the distance here is 1 meter. The distance here is 1 meter as well. Okay. We will be able to solve for the problem using sigma Fy, sigma Fx, sigma moment, because all the dimensions are complete, and we have all the equations as well. Okay. And anyone here can help me to solve this particular problem? We have 3 unknowns, remember, okay? Because Fx and Fy is not yet known, the value of the value of both, okay? F2 as well is not yet known. So we have 3 unknowns. 3 unknowns, Fx equal to 0, Fy equal to 0. Actually, it's better for us to not name it as Fx, Fy. If the name of the joint is A, I will name it as Ax and Ay. Ay, Ax, okay. Okay, sorry. So we have 3 unknowns there. Ax is not yet known. Ay is not yet known. F2 is not yet known. And we have 3 equations to solve it. Sigma Fx equal to 0, sigma Fy equal to 0, and sigma moment equal to 0. If we have 3 unknowns and 3 equations, will we be able to solve the problem? Anyone can help me to answer this?
Is it just tan sin 45?
Sorry, Alberto. Yeah.
Is it just tan sin 45?
Tan sin 45? No, not necessarily. You have to use all of these equations to solve for them.
Okay, I don't know.
Wait a minute, I lose my stylus. So how can we solve this? Can we solve this or not?
Can we solve it from Ax first?
Can we solve it from Ax first? Yes, you can. You can solve it from Ay first. You can solve it. Try to solve it for F2 first. You can as well, Marsha. Okay. So basically, there are several ways to solve it. Yes, correct, Marcia. You can solve it from Ax first. If we want to find out all of these 3, you can solve it from Ax first, or you can solve it from F2 first. Okay, Marcia. If we want to solve for Ax, what we supposed to do, Marcia?
Maybe we can move the force from F1 to Ax.
Nah, you don't have to move the force anymore, actually, this one, because this is equilibrium. When we talk about equilibrium, right, the total force in the x direction is handled by this equation. The total force in the y direction is handled by this equation. And beside that, okay, the total moment is handled with this. So basically, when we try to solve equilibrium condition, most of the time we don't have to move the force anymore, Marcia, because sometimes it will only complicate the problem, but sometimes yes, it will simplify the problem. Without solving the without moving the force, actually, you can solve this using sigma Fx equal to 0. Okay, sigma Fx equal to 0 means that the total force in the x direction will be equal to 0, right, Masya?
Yes, sir.
Would you mind to let me know what forces which is going to the x direction?
The F1.
F1, okay. So we have 10 Newton. So for example, positive is like this, okay. This one is positive. Okay, X positive is like this. Okay, so we have 10 Newton. And what else that we have?
AX.
AX plus AX. Okay, so that's the total force in the X direction. And the total force in the X direction is supposed to be equal to what?
Equals to 0.
0, correct. So this is our first equation. Can we solve AX? Yes, we can. AX is equal to minus 10 Newton. Correct, right, Marsha?
Yes, sir.
What it means by minus 10 Newton? It means that our drawing is wrong. So AX is supposed to be going the opposite of what we draw there. So instead of going to the bottom right, it's supposed to go to the top left like that. But it's okay, we know about it. So we solve for AX. Then we can solve for other force as well. Okay, we can solve for other force as well. Using sigma moment at A equal to 0, I believe we will be able to solve for F2. Okay, sigma moment at A equal to 0, I believe we will be able to solve for F2. Okay, Muhammad Hilmi Hakim.
Yes, sir.
Oke, saya minta tolong untuk kamu menggunakan sigma moment di A sama dengan 0 untuk mendapatkan nilai dari F2. Gimana, Hilmi?
Hitung momen yang F1 dulu.
Hitung momen yang gara-gara F1, betul ya? Kalau momen gara-gara AX sama AY bagaimana?
0.
0, karena kita center of rotation-nya ada di A ya?
Ya.
Betul. Jadi, yang akan menyebabkan momen hanya F1 dan F2 saja. Kan?
Ya.
Oke, sekarang sigma momen di A sama dengan 0. Akibat F1, momennya besarnya berapa?
10.
10 kali 1 ya berarti ya? 10 Newton meter, seperti itu ya. Oke, lalu anggap bahwa clockwise positif. Ya. Akibat F2.
Oh.
Akibat F2, momen akibat F2, besarnya berapa?
Minus 10.
Minus 10. F2 nggak diketahui loh. Kita tuliskan dulu ya. Ini arahnya minus kan ya. Berarti arahnya counterclockwise, jadi minus. F2 dikalikan dengan 1 meter kan ya? Betul nggak?
Ya.
Oke. Dan total momennya harus sama dengan 0. Seperti itu ya?
Ya.
Nah, dari sini apakah kita bisa temukan nilai dari F2?
Bisa.
Bisa ya. Jadi F2 kali 1 meter dipindahkan ke kanan. Lalu kemudian kita bagikan 1 meter itu ke 10 Newton meter. Jadi kita dapatkan F2 nilainya adalah 10 Newton ya.
Iya.
Betul ya. F2 10 Newton. Oke. Artinya 10 Newton di sana artinya adalah arah yang kita tunjukkan dari awal sudah benar. Jadi arahnya ke arah kiri bawah seperti itu. Oke, F2 sama dengan 10 Newton arah kiri bawah. Oke. Nah, sekarang Hilmi, satu lagi. Yang belum kita solve yang mana, Hilmi?
Yang A ya, Pak.
AY. Oke, AY. Nah, persamaan yang kita belum gunakan di antara 3 persamaan ini apa lagi?
Sigma F ya.
Sigma FY sama dengan 0. Nah, bisakah itu kita gunakan untuk menyelesaikan AY?
Bisa.
Nah, kita pakai persamaan ketiga kita ya. Sigma FY sama dengan 0. Nah, dari sigma FY sama dengan 0, gaya-gaya apa saja yang arahnya ke Y di sini?
F2 sama A ya, Pak.
F2 dan IY. F2 nilainya sudah diketahui ya. 10 Newton positif. Oke. 10 Newton. Lalu IY arahnya sama juga. Kalau kita anggap bahwa ke kiri bawah itu positif, ya, berarti 10 Newton ditambahkan dengan IY sama dengan 0, gitu ya.
Ya,
Oke. Nah, nilai IY berapa sekarang?
minus 10.
Minus 10 Newton. Oke. Terima kasih banyak, Helmi. Ya. So we can see here by using these three equilibrium equation, we can solve these three unknowns: AX, AY, F2. Okay, F2 is 10 Newton, which means that the direction there is correct. So F2 is going 10 Newton to the bottom left. AX is minus 10 Newton. Minus them, which means that the direction is the opposites of what we draw. So instead of going to the bottom right, it's supposed to go to the top left, 10 Newton top left. Okay, AY is the same, it's minus, which means that it's supposed the direction there is the opposite of what we draw. So instead of 10 Newton to the bottom left, it's supposed to be 10 Newton to the top right. Okay. So that's how we solve for equilibrium. Okay. For two force member and three force member, I will explain it later because I believe if I explain it now, it will be too much. Okay. So this is what we have done in the previous problem example. Okay, when we want to solve equilibrium analysis, the first thing that we're supposed to do is to draw a free body diagram. Remember just now? The first thing that we do is drawing this free body diagram, okay, from the problem. So the first thing is to draw the free body diagram. And remember that free body diagram only consists of the body that we try to solve and all the external forces, okay, all the external forces and the gravitational forces which is happening to that particular body. Okay, after drawing the free body diagram, try to identify the known and the unknown variables. Okay, for just now, we know that, oh, the known variables is F1. F1 is 10 Newton. We know the value already, 10 Newton. But for AX, AY, and F2, those three are the unknowns because we don't know the value yet. So we have three unknowns, AX, AY, and F2. Then we implement first and third Newton's law. In this case, it's equilibrium equation. Sigma Fx equal to 0, sigma Fy equal to 0, and sigma moment equal to 0. This one. And then try to find solution by implementing those three equilibrium equation. So those are the step-by-step to solve equilibrium problem. Okay, I believe it's clear enough for you guys, right? Actually, the basic of solving equilibrium condition is just like that. But like it or not, we have to practice because practice makes perfect. And I believe some of you still a bit blur about some things that I taught you just now. So keep practicing and don't worry about this. Next week as well, we will still talk about equilibrium. Okay, we will still talk about equilibrium next week. Because practicing about equilibrium, it takes quite a while, especially on how to draw the correct free body diagram. Okay, let's make this as our last practice. Okay, previously we talked about two-dimensional free body diagram, which is not having a force happening at the same point. Okay, so this one is considered as a general condition. General condition, okay, like this. I will try to show you the condition of this one. Concurrent at a point, which means a point equilibrium. Okay. This is the example of point equilibrium. Okay. 3 cables are joined at the junction C. Okay. Determine the tension in cables AC, BC, caused by the weight of a 3 kilogram cylinder. Okay. Remember there is a pulley here. Okay. If you have 3 kilogram force, what do you know about this? How can we draw the free body diagram? Anyone here can help me? Hello? Anyone? Hello, Judy. Since you were gone the last time I asked you for this particular problem.
Okay, sir.
Okay, what happened with you?
My internet got disconnected.
Okay. So, in order to solve for this particular problem, what are we supposed to do, Judy?
I think first we have to draw the free body diagram.
Draw the free body diagram. Which free body diagram? That's the most important thing as well.
I think free body diagram for the mass.
Sorry, free body diagram for the what?
For the cylinder.
For the cylinder first. This one, you mean? You mean this one? Okay.
Yeah.
How can we draw the free body diagram for that cylinder then? That's the first one. Actually, it's correct. What we have there.
First, we have to identify the forces.
Correct.
Acting
What
on
are
the
forces
cylinder.
which is happening to that cylinder, Judy?
We have tension and weight.
Yes, correct. We have tension force. This one is tension, T, and the weight. The weight, we put it at the center of gravity. What is the weight there?
30 kilograms times 9.8.
Yes, correct. 30 kilograms times 9.81. Okay, meter per second. Okay, because we are running out of time. In order to simplify this, most of the time you're supposed to use 9.81, okay? But because we are running out of time, in order to simplify this, I use 10. So we have 300 Newton here for the weight, okay? Using, because the force which is happening here is on the same line of action, then we can use sigma y equal to 0 to solve this. Correct, right, Judy?
Yes, sir.
What is the value of T then? It's supposed to be T minus 300 equal to 0, right? 3T minus 300 Newton equal to 0. So T is supposed to be 300 Newton. Okay. What's the next free body diagram that you're supposed to draw, Judy?
I think for the cables.
The cable or the pulley?
The pulley D, yes.
Pulley D, correct. We can draw free body diagram at pulley D. So we draw pulley D there. Okay. Because it's action and reaction at this particular line, at this particular cable, at pulley D is supposed to be going down, tension going down. Because it's action and reaction with the cable here. Okay. So what else that we have is we have another cable here. It's, maybe we call it as T1 here. T1, this one is T2. And what else that we have there? Okay, because this one is still example, I will draw it for you guys. At point D, okay, there will be a reaction force from the pin. So we will have dy and dx over there. Okay, but remember, dy and dx is not asked in the question, so we don't have to solve that. So we can solve for T2 using sigma moment at T equal to 0, because T1 is known already here. T1 is 300 Newton. Sigma moment at T equal to 0. What we will have is 300 Newton from T1 multiplied by the radius minus T2 multiplied by the radius equal to 0. What we will have is T2 equal to 300 Newton. So now we know the tension here, T2. Okay, Judy, after we know the tension T2 there, the question is the tension at AC and BC. What we supposed to do next then?
I think also another free body diagram on point C.
Correct. So we have to draw this ring, right, at C. Okay, so now we try to draw the ring at C. What forces which is happening there? The first one that we know is T2, right? Yeah, T2 going that way, because action and reaction with this one. What else that we have, Judy?
Tensions in the cable BC and AC.
Okay, BC, because it's tension, I will put it like this, FBC and AC. The direction is supposed to be the same with the cable, okay, FAC. T2 is known, T2 value is 300 Newton. Now, can we solve this, Judy?
Yes, we can do the summation of forces, the
Summation of
total.
forces.
Yes.
Or we can use this one, sigma Fx equal to 0 and sigma Fy equal to 0. Because all the line of action will meet at one point, right? So actually, this one is the same as this product, concurrent at a point. In that case, the equilibrium condition that we can use is sigma Fx equal to 0 and sigma Fy equal to 0, because the moment will be 0. There will be no moment there. Okay, Judy? Okay, we can solve it using this. Sigma Fx equal to 0. Then sigma Fx equal to 0. Sigma Fx equal to 0. What we will have there will be 300 Newton cos 15 degrees. Remember this one? It's 15 degrees. Okay. Going to the right positive, minus FAC cos 45 degrees minus FBC cos, sin in this case. This one is sin as well, sorry. Sin 45 degrees, sin 30 degrees equal to 0. That's your first equation. The second equation is sigma Fy equal to 0. Sigma Fy equal to 0, what we will have there is 300 Newton going up positive, sin 15 degrees plus FAC cos 45 degrees minus FBC cos 30 degrees equal to 0. So we have these two equations. Using those two equations, okay, we have two unknowns there, right? FAC and FBC. Will we be able to solve FAC and FBC there, Judy? Using those two equations.
I think we can, two equations, two unknowns.
Yes, correct. We can solve it. as long as you just multiply it with all the cos and sine, okay, then using substitution and elimination, you can solve for FBC and FAC. So that's the way to solve this particular problem. Okay, there are 3 free body diagrams that we're supposed to draw. Okay, this one is just introduction to the equilibrium and free body diagram. Okay, remember to check the EduNext, because my assistant already posted the homework for next week. The due date for the homework will be before our class on Thursday, so 10 a.m. Thursday. So that's the deadline for the homework. So you're supposed to submit it before that. Okay, and next week we will still talk about equilibrium. Okay, I think that's all for today. See you guys next week. Okay, thank you very much for listening.
Thank you, sir.
Yep.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Have a good day.